Hi Manuel, thank you very much for sending me your Module 1 assignment. I'm just going to narrate over your slides now so I can give you some really immediate feedback on what you've done. Okay, nice little summary here. Just be aware that I don't think this is going to fit in a lesson. I assume you mean unit here. Okay, so just having a look at your description of efficiency here, I would avoid the word amount. We tend to a lot in science because it's very vague. It's probably better to refer to either the percentage or the proportion instead. So the percentage of energy which is useful compared to the amount of energy which is put into the system. And again, really nice you've got the efficiency for equation in both terms of energy and power, which is great. Just watch capitalizations here. It's a small thing, but when we're preparing resources for children, try to model good quality English as well. That's a teacher's requirement. Again, here we've got power is energy transferred per second. Just watch out for that. I think it's better to give the proper definition of power, which is the rate of energy transfer. So whenever we're saying, per division of time, we try to use the word rate there. And then here we've got the equation can be expressed as decimal fraction or percentage. Absolutely right. And again, less than or equal to 100%. And again, if you're talking about decimals or fractions, you can also say or is got to be less than or equal to 1. Okay, bullet point 1 looks good. Bullet point 2, just watch this because it sort of loses a bit of sense. I think what you're trying to say is that efficient appliances transfer the least proportion of waste energy. I think we want to try and stick with using that word proportion because it's better than saying amount of waste energy. Because it depends, obviously, it is about the proportion of what's going in. And then when you say the rest of the energy, I think what we need, it's sort of, you're talking here about in bullet point 2, about transferring waste energy, and then you're saying the rest of the energy. I think what you mean to say is that useful energy gets transferred and then the remaining energy is wasted and it's lost as heat. Or sound to the surroundings. So just watch that sense in these 3 bullet points here, because if this was a class slide, I think this would really confuse the students. Then looking at your activity, lovely, and it's really nice how you model that calculation and how to lay it out there. Yep, this all looks very good, and particular explanation about why conduction is good in metals. Just one thing here, when we say does conduction mostly happen in metals, that's a bit misleading. Conduction happens in any solid, but conduction is faster in metals. So just be careful here because that makes it sound as though things like plastics or ceramics don't conduct, and of course they do. So maybe it's better to say why does rather than why do, why does, and again, no capital letter here. Why does conduction occur more quickly is probably better in metals. And then you can talk about this idea that metals are more conductive or have higher conductivity. So just watch out with that. Otherwise, your explanations here are really good. One thing I quite often do when I'm teaching this topic is before I get onto conduction, I talk a bit about the laws of thermodynamics and this idea that heat energy always goes from hot to cold. And that's really useful when we start comparing conduction and convection and radiation, because when you're talking down here about being transferred down the spoon, actually the direction isn't up or down the spoon, it's from the hot end to the cold end. So actually with most examples, if I've got a spoon in a cup of tea, actually the hot will go up the spoon from the hot drink in the bottom of the cup up along the spoon towards the hand. So just watch out when you're talking about directions here. Here's an example of a slide I use for this lesson, and as you can see, I'm just laying out here a little bit more about metals are good conductors because they also have free delocalized electrons. I've also mentioned here that different metals conduct at different rates, so hopefully you might find that useful. Okay, so there's again a few things here we need to sort of iron out. You talk here about the particles being less dense. Particles can't change their density, so we need to get rid of that. That really is a massive misconception. So if I'm thinking about a liquid, if I think about drawing a box with a liquid in, the particles are going to be close together, they're touching, but the particles are just a little bit more irregular. They're going to be able to slide past each other, so they're not quite the same as a solid where they're in fixed positions. But the particles, the individual particles themselves, we don't measure their mass and volume because that doesn't change. So they can't become less dense. Instead, as if those particles spread out, then that area of liquid or gas becomes less dense. Okay, so again here we can't say the particles become less dense because that doesn't happen. You've correctly mentioned here about the convection current. I'm just going to show you the next slide and see if that gives you a bit of an idea of a better way of putting it. So this is part of a series of slides that I do when I'm looking at convection, and you can see here I talk about the fact convection is how heat energy is transferred through liquids and gases and refer to those as fluids. And I also explain that it doesn't work, conduction won't work in fluids because the particles slide past each other. So I start off by getting the students to think about why conduction won't work. And then when I'm writing the explanation, I talk about this idea here that particles near the heat source vibrate and spread out, forming an area of less dense fluid. So I'm not talking about the particles changing density because that's not true. I'm talking about the fluid, the gas or the liquid changing density, so it does become less dense. That area then rises. You can also use the word float. Doesn't hurt for them to make the link with buoyancy. And then cooler, more dense fluid sinks. And again, here I'm referring to cooler, more dense fluid, not about dense particles, because that would be incorrect. And then it sinks and replaces it. Hopefully that makes a bit more sense. Okay, nice reference to no particles required, and it's the idea of heat energy as infrared waves. That's nice. And in fact, you can make a link with year 7 work here that it is an energy pathway. I like bullet mark 3, this idea that the hotter the object, the more infrared radiation it emits. Number 4 is lovely. Number 5 is lovely. Just watch here. The sun heating the earth is a great example because we know that there is no solid, liquid or gas in space between the sun and us. Therefore, the only way that heat energy can reach us from the sun must be radiation. A campfire, I don't think is a great example because you're saying you can feel the heat even if you're not touching the flames, but of course it can be convected. A better way of talking about that is if I've got a fire or a flame or a candle, convection is how the heat energy rises with hot air or hot fluid. But infrared radiation radiates out in all directions 360 degrees. So a better way of using that example of the campfire is to say, we all know our hand would be hot on top of the campfire. What we don't always think about is the fact that some of that energy is coming out at the sides. And of course, that can't be convection because with convection, the heat energy always ends up going in a direction upwards. And you can demonstrate that with a candle. Okay, Sankey diagrams are an interesting one because some boards still use them and some don't. So you're correct, it is a scale diagram, that's important. And again, it does show the useful out and the wasted out. I like the fact you put the wasted going down because you sometimes see some which are incorrect where they have the wasted at the top and the useful at the bottom. I'm just going to put 2 other examples up on the screen so you just see perhaps a way that I quite like to demonstrate them when I'm looking at Key Stage 3 in particular. What I like about this one is you can really clearly see where we are measuring those different widths, and I think that can sometimes help a little bit. So you can actually see that you could measure this width here. Oh, it's quite hard to draw on here, and this width here. And if I were to add those 2 widths together, it would be the same as the whole width. And in fact, to make that even clearer, This one here, which is done on graph paper, is even better because you can literally count the squares. The fact that you've got 10 squares here, 9 squares here, and 1 square here. So you can see that the 10 splits into 9 plus 1. So when I'm teaching, I tend to start with the one I've done there in orange, and then depending on the board, then use the graph paper and get them to practice scale drawings. But when you come to teach, you may or may not need to do them. Our board doesn't actually use them anymore. Yeah, this is fine. Again, the only thing I would suggest is either show the widths or do it on graph paper just to make it really clear that the width going in is equal to the sum of the widths going out. It's just slightly easier to see it on graph paper. Okay, so it's really nice to see you put a practical investigation in here. I think what is important to think about though is what the investigation is for, because you seem to be suggesting here that you're looking at conduction, convection and radiation. I think that's quite difficult to do in one practical, and I certainly wouldn't. You then here in number 2 said how effective, let's get rid of that S there, are different materials as thermal insulators. That seems to me a better one because you're now identifying an independent variable. So you're going to change the materials, and then you're looking at reducing unwanted energy transfer. So we now need to identify a dependent variable. And you've looked here at what the independent variable might mean. So you've looked at the fact it could be these different materials. Okay, looking at your method then, nice to identify the hot water hazard. Again, you said pour the water into a beaker. You really need to say what the volume would be. It's really important that along with the independent dependent variables, we're identifying the control variables or what things they should be. So you need to specify a volume here. Record the initial temperature good here. And again, when I'm teaching the students earlier on, I'd say what with. So I'd say record the initial temperature with a thermometer. And then recording every 10 minute for 10 minutes, brilliant. And then repeating with different insulating materials, that's lovely. So just be aware that when we're teaching, we're constantly thinking about the independent variable, so what we change on purpose. Okay, which in this case is obviously the materials. The dependent variable here is going to be the temperature change. Okay, so that is what changes as a result, and then we need to identify our control variables, and that's what we're going to keep the same, which in this case is going to be the volume of the water and the amount of time that you are letting the water cool down for. You might also then discuss with the students, if you're doing all these different materials, so foil, cotton wool, bubble wrap, newspaper, are you attempting, for example, to keep the thickness the same? You might not, but that gives you a really interesting thing to talk about with the students then. Okay, I like this nice discussion about practical and how we'd use it and some of the things that you might do, particularly that idea of flexibility for children choosing their own materials. Okay, that's great. So a couple of bits there then. I think with the investigation that you were looking at, this is really about insulation. So I would normally explain what insulation is before I do one of those practicals. And I would talk about this idea that insulation reduces the rate of heat energy transfer. This is a couple that I do. This is a lesson I do in year 8. And as you can see there, we look at the methods rather like you have. And just to sort of bring up a few points that I think are useful. For example, up here, we mention exactly what the volume of water is, and we talk about some of the equipment that we would use. We emphasize the idea of finding the change in temperature or plotting a graph of the change in temperature. And then I would make sure that the students identify the different variables. And in this case, if I'm just doing temperature change and material, then I would be plotting a bar chart. So in this particular class, we did a bar chart rather than a temperature cooling curve. And then again over here, I'm repeating it, but I'm using a lid instead rather than different kinds of material. And this time, again, I'm getting them to identify the different variables. And then what, in this case, we used a bar chart. The reason this is useful is I can then point out that this particular practical here is looking at reducing conduction because we're using materials which have different conductivity, and this one here is looking at reducing convection because we're either putting a lid on or not a lid on. And I can do a third one where they wrap the beaker either in black card or silver foil, and then we can look at how they reduce radiation. So like I was saying earlier on, the more we split up these different ideas, the more easy it is for the students to pick it up. So I hope you find that useful, but this is the sort of thing that I regularly do with my Year 8 classes. Yes, some nice safety points here. You're absolutely right. Teachers do have to plan the safety before they start anything. And again, technicians, TAs would support as appropriate. Just watch out for the apostrophe here. There's no apostrophe in equipments because it's a plural. And again here, and again, just watch these things. If you know you stumble on these, double check them because we are modelling English for children, and that's one of the teacher standards. Okay, this is a big misconception there. That's definitely not true. This is better. Non-renewable is a finite energy source. It will eventually used up and can't be replaced. Or we quite often use the word replenished. That's very common now in certainly the AQA syllabus. Renewable energy are those that will run out. We don't use the word natural because things like coal, oil and gas are natural. You know, they were formed millions of years ago. So this idea that they are unnatural and hydroelectric is natural is something we really need to stamp out with students because everything's natural. It all comes from the earth. You've absolutely got all the right ones in the right places. So solar, wind, hydroelectric, tidal, geothermal and biomass. And it's quite nice at this point to remind students that biomass includes wood because they quite often forget that. And they're non-renewable energy, often release greenhouse gases. That's true, but be very, the fossil fuels do, but nuclear fuel is not a fossil fuel. Okay, so not a fossil fuel. It's really important because when we're talking about fossil fuels, they need to understand that uranium is not burned and it doesn't release carbon dioxide. Because when we are talking about how we decide which energy resources to use, children need to understand that some countries choose nuclear because it is less polluting in terms of carbon dioxide. Okay, so it's really important we make that point. Yep, great. Again, just watch those capitalizations. It should be a small p there. Again, we're just modeling for students. Yep, that's all good on here. One thing for you to be aware of is that we're now required to teach about energy stores and energy pathways. So kinetic energy will be considered an energy store. And therefore, when we talk about energy stores, we can talk about them increasing or decreasing. That's quite good language to start using with students as soon as possible. So for example, an accelerating car would have an increasing kinetic energy store. Yep, following on from last slide, these all look perfect. And again, these are perhaps more obvious energy stores, gravitational and elastic energy stores. Students will have met these before as well. And again, this is great. You've got the full list here. Again, thermal and chemical students will have met at Key Stage 3. They may or may not be familiar with the last three because they're a little bit more unusual. Yep, these are all correct. When you come to teach later on, I have a bit of an issue with this one because sound waves are not transferred in the same way that electromagnetic waves are. You've got the syllabus correct, but actually we model sound waves as mechanical waves. So I must admit, when I teach the children, I teach them about radiation. I talk about infrared radiation, going back to what you spoke about in your earlier slide. I talk about light, and then I talk about sound separately. Again, because otherwise I feel like I'm setting up a misconception for later on in their lives. But yeah, this idea that that energy is transferred, you may see these referred to as pathways. depending on your syllabus, but certainly at Key Stage 3, they quite often refer to these as pathways. Yeah, these are fine. What's your capitalizations again? Okay, so just be consistent. This one's fine and this one's fine. This is a slightly old thing about teaching energy stores and pathways, which I find doesn't really work, because there's nothing wrong with what you put in the other 2 bullet points, but with the new way of teaching, they like to show a store of energy moving to another store of energy. It makes it very clunky. So with the first and fourth examples, it works fine. A chemical energy store in the man's muscles to the gravitational energy store as the weight is off the ground. And again, the kinetic energy store, the wheels, the thermal energy store of the friction. But with the other ones here, you've got a mixture of pathways. And I'm not saying that what you've written is incorrect, because I don't think it is, but you won't see that. I think the exam board is sort of avoiding it by just not putting those examples in. But so yeah, I don't think they're wrong, but you probably won't see those. It seems to be a new way that they want us to sort of explain things. Yeah, this is really nice. I always like to see examples of calculations, and I really like the way you've modelled it, laid out your working. This is exactly what we want the students to do. And I make a big fuss that they do this in their books every single time, that they write out the equation, put the numbers in, get the answer, get the units. So absolutely lovely. Yeah, really lovely this. Very clear, and a really nice sort of discussion point here that we talk about energy being lost to the surroundings, and what we mean is it's become less useful. So yeah, really nice. Okay, lovely that you used the word rate here, really nice, and the fact you've referred to SI units, which is great. There's no apostrophe here because this is it's possessive as opposed to it is, which is where the apostrophe goes. This bit here, watch out. This first bit is absolutely fine. This bit here, you're muddling up a discussion about power and a discussion about efficiency, and they're not the same. So you need to be very careful about that. It is true that less powerful items transfer less energy per second. So a 10-watt light bulb is transferring less energy per second than a 60-watt light bulb. So we are using less energy, and therefore it will cost us less, for example. However, efficiency, remember, is the proportion of useful energy. So for example, if I had a 60 joule or 60-watt light bulb, which was 90% efficient, is that better or worse than a 10-watt light bulb, which is only 20% efficient? So I would not put those two things in the same sentence, because you're not comparing the same thing. This is power, this is efficiency. And the moment we start muddling up, the students will start thinking it's the same thing, and it's definitely not. What's your capitalization here? So yeah, this is fine. Yes, a higher power kettle will boil water more quickly. Okay, good stuff. Yeah, this is all good. It's usually worth at this point explaining why we use kilowatt hours, because the students won't necessarily realise. And of course, it's that whole idea that it makes the numbers smaller and more manageable, because if I get the answer in joules, it's going to be horrifically large. And of course, what I'm doing is, in effect, dividing every power rating by 1,000 and every time in seconds by 3,600. So it's just that idea we're getting manageable numbers. Yeah, I think it's a nice point you make there in the bullet point, and your activity links with that really nicely. Just a shame you didn't do a nice little example here like you did on the other slides, because that would have been nice to see that working out, but it's a good example. Yeah, some nice points here like that. And absolutely agree with this one here. Modelling is always really good. I think this is really good, either having the data sheet or when I've had my own classroom, sometimes I've had the equations up on the front, and it's quite good watching the students learn to look, and of course that helps them learn them. Absolutely love this one. Yeah, keep on at them for that forever and ever and ever. I make mine redo everything if they don't do that. It's just really, really good habits. And yes, very nice here. I particularly like the idea that we're looking at these data forms, so checking units. It's something which, particularly at GCSE, they get a bit lazy about. They don't think to check those sorts of things. So really nice points. Yeah, good. Again, what's your capitalization here? Because you don't need it. But we do here because obviously it's his name. Yeah, excellent. You'll soon find as well that they are terrible at modelling up for Mr. and variable resistor. So yeah, these are all the ones they need. Perfect. Yeah, again, very nice putting these. So you've got the definitions alongside all of the symbols. Just watch, only allows current to flow one way. Good stuff. I'm really glad to see you found PhET. It's a really nice tool. And interesting because, of course, you can get them to do this, which is the drawings, and then you can get them to do them as circuits as well. I try and get them to do them as circuits so they get into the habit of using those symbols that we've taught them. This is an interesting one. The conventional current flows from positive, and you can certainly see that on PhET. It's really worth spending a bit of time explaining to the students that that is convention. It's not what really happens. There's a really nice activity you can do where you give them a bulb and a battery on one wire and try and get them to tell you why that incomplete circuit won't allow the current to flow. And we can talk about this idea that the electrons in effect are repelled from the negative terminal and attracted back into the positive terminal. And then we can go back and talk about convention being wrong because it was set up before people really knew about electrons. So plus to minus sort of made sense. But yeah, really love the use of PhET. Yeah, nice use of the word rate here. So we're linking back to what we've done before. And then nice to link the equation to the definition, which is great. I'd watch out with this bit here. I don't like the word it anyway, because we tell the children not to do that. The electrons aren't carrying current, they are the current. So it's the rate at which those electrons or charges are flowing through the wires that we call current. So just be careful of that. Charge, yeah, and it's useful here to just sort of, I quite often tell them that the charge on one electron is 1.6 times 10 to the minus 19, or just very, very small at GCSE. And it's just to make the idea that we don't count the number of electrons because we'd be there all day. We use this coulomb, again, a bit like kilowatt hours. It's a more manageable number. Charge equals current times time, lovely. That rearrangement of the original equation is great. Yep, nice example again. And again, I love the fact that you lay out your calculations beautifully, which is great. And you can mention that the ammeter is here because we need the current to flow through the ammeter if we're to measure how fast it's traveling. So it's a bit like putting your hand in a river of water. You can tell how fast it's moving if you stick something in. So it's really good early doors to make that point. Yep, nice what you said here about potential difference, and nice that you use potential difference first and then refer to voltage. And just so you know here, I use the word across, but now a couple of the exam boards are saying the voltmeter is in parallel with the component. I mean, it's the same difference, but I try and get that language in a little bit as well, so I'm matching what the exam board says. Yeah, resistance, opposition to flow, charge, good. And I like this bullet point here. I get the kids to practice that a lot because they really don't get the idea that the increase in resistance means a decrease in current. So that's really good. I usually stick the little omega symbol in here so they remember what that one is. And very nice that you've made this point at the bottom. Okay. Yeah, you don't need to capitalize here, but it is consistent, so I'm less worried about it here. This word linear, you're absolutely spot on. Assume the kids won't know what that means. The math syllabus and the science syllabus don't necessarily work together. We sometimes find we're teaching stuff in science before they've learned it in maths. So I would demonstrate that either with a little practical and getting some results or just by doing a graph. Interestingly, we do an IV graph at GCSE because it's the dependent variable is the current and the independent variable is voltage. Although, of course, once we get to A level, we swap it around for Ohm's law. So I would actually get something where I've got a straight line and just talk about the idea a linear relationship is a straight line. And in fact, what we've actually got is a relationship which is directly proportional because it's a straight line through the origin. So it's more than just linear. The earlier we get in that, the better, because there are lots of relationships, obviously, that they see in physics which are directly proportional, and they do get asked about it. And again, nice showing the rearrangement there, and a nice example. Yes, nice summary here. Just a couple of bits that you might find useful. So you've said here the ammeter goes in series. I'd pop one on here. I know it's not the easiest thing to draw. If you have a look on Google Images, you quite often find examples of simple circuits like this. You don't have to draw them, you can just copy them. So I'd always recommend that. This one's really nice. I like this. This is, in effect, Kirchhoff's laws. You might want to think about how you'd explain that to children, because they may not get that to start with. But it's that idea, if the current's the same all the way around the circuit, at any point in the circuit, then the current flowing in must equal the current flowing out, because otherwise we'd have sort of some weird bunching up of electrons, which we know doesn't work. So you are absolutely right. Just think about how you might explain that when you come to teach it. Just watch capital V for volts, because that's somebody's name. And just make sure that when we say it's shared between each lamp equally, that's only if the lamps are identical. Okay, because we look at lots of real world examples where they're not identical, and therefore the potential difference isn't shared equally. It's shared depending on the two lamps. So we do have to say it's only shared equally if the lamps are identical. So for example, if this were 12 volts here and this had 4 volts across it, this would be 8 volts. So it is shared but not equally. So hopefully that makes sense. Yeah, again, lovely summary. And one thing you might find useful when we're thinking about this idea here, I always say to the students, I can tell if it's a parallel circuit because there are junctions. There are places at which the current can go one way or the other. And it's useful to get them thinking like that, because some real life examples they may have to look at might not look as nice and obviously parallel as this one. So you talk about branches, that's lovely. That branch happens where we get a junction. So that's quite useful to talk about junctions. And therefore, when we're talking about current being shared, what we really mean is it splits, because again, we have to be careful they don't think shared means it's shared equally, because again it depends on what we've got. So for example, if I've got something like, say, 6 amps coming up to this junction here and 2 amps goes in this direction, then I must have 4 amps going in this direction. And so when the current gets to the junction, it splits, and then when it gets to back to this junction here, if I've got 2 amps coming in this direction and I've got 4 amps coming in this direction, they join back up to make the 6 amps that goes all the way through the battery. So it's that idea of the current splitting. And again, when I talk about my Amazon vans, I say if I sent 6 Amazon vans out for the battery and 2 turned left, 4 are left, so 4 will go straight on. And then when they come back towards the depot, 2 arrive here, 4 arrive here, I end up with 6 vans going back to the depot. So I sometimes give them that idea that when we talk about the current, we might be talking about, you know, in this case, number of electrons carrying that energy, if you like. Resistance doesn't add up, absolutely right. At GCSE, they are required to know that putting 2 in parallel gives an overall result of half the resistance. So when you come to look at GCSE, have a look and see what your particular board requires you to teach them about parallel resistors. does change from time to time. And again here, net current flowing through the circuit altogether is shared by the branches. Yes, that's true, because you've got the net current here is 6 coming out of the battery and 6 going in. Again, just be careful about this word shared. I prefer to talk about what's going in and out of a junction. And Kirchhoff's law tells me that the current going in must equal the current going out. It's another nice sort of conservation of charge. What goes in must come out. And then this is lovely here, always equal. Lovely. I really like the fact that you've taken the time to explain where the equation comes from. So this idea that we're substituting in and then reworking our equations to get to E equals VQ. I think the more that children, certainly higher tier children, see us manipulating algebra, the better, because it's not a great strength for them at GCSE in particular. I think it's really good to do that. So yeah, absolutely do this all the time. It's really good. Okay, lovely. And of course here, what we've just done is identified our independent and dependent variables, and they would definitely need to be able to do that. So the idea that we're changing the length, which is our independent variable, and we think that as a result, the dependent variable resistance will change. Directly measured. Careful, we don't directly measure resistance. Okay, because in here you're using an ammeter and a voltmeter. So actually what you're measuring is you're measuring the current and the potential difference, and then you're calculating the resistance. We are directly measuring the length though, so just watch that. I would always get them to set up a circuit diagram as well to show what this is going to look like, because we need to show the ammeter, we need to show that length of wire, and then we need to show that the voltmeter is measuring the PD across the wire. Again, quite often they'll do the PD across the battery, which is obviously not what we're measuring. So it's worth having that in there as well. Little p there. Calculate resistance plot length against resistance graph. Good stuff. Use low voltage. Good. That's a really good one, because otherwise they burn through the wires. Lovely. Nice stuff for safety. That's really good. And of course, safety and accuracy, because if the wire gets hot, it might affect the results. In reality, we tend to use Constantan wire in school, which doesn't change its resistance with temperature much, but it is a really good thing for them to think about. Okay, this all looks good. You're absolutely right to sort of highlight the importance of these required practicals. Not an apostrophe there because it's not possessive. And again, we don't need a capital there. All boards and examinations. I would agree that doing circuits is best delivered. I would usually do it in pairs if I can, and again, try and make sure you get them to think as much themselves as possible. I would agree, and again, I'd agree if you can have sets of results in case students struggle or they're away, that could be useful. I try to persevere getting them to figure out practicals or supporting them to learn how to do it. I spend a bit of time teaching them to fault finding electrical circuits, for example, because it's a really useful life skill. I don't think we spend enough time on it. And again, really nice stuff there about hazards. Yeah, all good. Again, I think you mean session rather than lesson, otherwise you're setting yourself an awful lot of work to do in a very short space of time. Yeah, nice showing a diagram and a picture. It's really useful that we make students go to diagrams rather than pictures. Not sure why that is under series circuits as opposed to just circuits in general. So maybe reconsider that one. Yeah, I think here you mean torch, and just make sure we don't capitalize. And again, I agree. I get them to do lots of circuit drawing, whether it's giving them a list of components to draw or whether I make a circuit and ask them to draw it. But going between real life and a circuit diagram is really useful for them. Yeah, all good. This certainly matches your descriptions from earlier on. That's good. This makes a little bit more sense now. I can see it. I think here, rather than talk about electrons, I would talk about current. Because obviously I don't know what an individual electron does. It might go through lamp 1 the first time and lamp 2 the second time. So I think it's about talking about what happens to current and then what happens at these junctions, the idea that the current splits. If we start talking about individual electrons, I think we're on sort of sticky ground, but we are talking about the fact that the rate of flow of electrons is slower in each of these two parts here because the current has split. Yeah, that's good. This is fine. I think it's okay at GCSE, but again, I think it's better to talk about current in equals current out. Okay, so if this is in and this is out, then the current in must equal the current out at any junction. It's a better setup for what they learn later on if they go beyond GCSE. Yeah, nice. And it's good to ask the students why those systems would be parallel. Again, just watch capitalization there. And again, yes, lots of practice drawing circuits. Okay, this is a nice example, nicely worked out. Just a couple of things for GCSE. We would need to state that the bulbs are all identical because otherwise we are making assumptions that they are. This wouldn't work if those bulbs weren't identical. And this equation here, certainly on AQA, isn't required. That's A level. So you may or may not need to use that. I don't know if it's in the OCR or Edexcel syllabuses. It certainly is at A level for all of them. But at GCSE, that wouldn't be required, certainly on AQA, which I think is the biggest board. Yeah, lovely summary. Great way of putting it. And I like this because that is what they do have to know for GCSE. Okay, so this is obviously the next required practicals. That's not really an aim. Really, what we're aiming to do is to understand how current and potential difference vary in series and parallel circuits. So I would have a think about your aim, because an aim of an experiment is not to use a bulb to investigate it. Just watch your capitalization here. We don't need to have capitals for all of those. Method. And again, this isn't really a method here because you're saying you're going to use your equipment to do these things, but actually we'd need to lay out a proper method for students. Safety is all good, yeah. And again, if I'm measuring, I'm not sure how I can measure brightness. We don't tend to get out lux meters. We don't have many of those in schools. They're very expensive. So I'm not sure what graph I'll be plotting here. I'm just going to put on the next slide perhaps the most common practical we do to look at series and parallel circuits, and then compare it to the one you talked about with resistors, which definitely is done where we're sort of building and doing measurements. We'll just go on to the next slide. Okay, so if I'm investigating series and parallel circuits, I would usually instruct the children to set up a series circuit, and I would ask them to put an ammeter in series in the circuit. I usually use a couple of bulbs, and I would then ask them to measure at point 1. I would then ask them to do the same here at point 2, and then I'd ask them to do the same here at point 3, and then I would ask them to record and compare the results. And of course, what we should see is they get the same currents. I don't know, they might get 2.2 amps, 2.3 amps, 2.2 amps, and then we can get that conclusion that the current is the same all the way around the circuit as we'd expect it. And I'd then get them to do the same experiment, but this time I would ask them to put a voltmeter across here, that would be V1. I'd ask them then to move the voltmeter to V2, and then move the voltmeter to V3. And again, getting them to move the ammeter and voltmeter is a good way of getting to practice building circuits. And again, I'd ask them to record and compare. And at that point, they should see that V1 equals V2 plus V3, or more or less. In reality, we get sort of slightly mixed results. And I then want to do the same sort of thing. I'll make that slightly less wobbly line there. I then want to do the same sort of thing with a parallel circuit. Okay, and again, I get them to set up the parallel circuit, put a couple of bulbs in, put an ammeter here on the way into the battery. And then I'd say I want you to measure the current here, and then here at 0.2 and here at 0.3. And this time, if I record and compare, I should end up with A1 equals A2 plus A3. And then again, I'm going to do the same, but measuring the potential difference across, first of all, the battery, and then each bulb. And then I would end up with, hopefully, V1 equals V2 equals V3. And so in terms of a method, I've now got 4 little experiments here. I might not even do them across one lesson, depending on the class. But then my aim is to understand how the current and potential difference vary in a series circuit and in a parallel circuit. And I'd want them to use these diagrams as part of their method and explain what they did in the way that I've just done. So I think when we're looking at writing up a practical we're going to do, we need to make sure that we're not just saying we're going to investigate with some bulbs. And as you can see here, the readings I'm taking are current and potential difference. It's interesting to compare the brightness of the bulbs. Of course, they're going to be much brighter in the parallel circuit but then what we can go back and say, well, if the voltage or potential difference is equal, then the amount of energy per coulomb is much higher. And that's why those bulbs are brighter. In my Amazon truck sort of model, each of my Amazon trucks might be going down different pathways, but they're all carrying the same amount of stuff in the truck. So each bulb gets the same amount of energy, if you like. But just be careful if we're sort of explaining experiments that we're really clear, and then make it even clearer still when you're talking to children. Okay, so this is our resistor experiment. Just a couple of things to look at here. I mean, again, just watch out some of the capitalization here. I'm not sure if you meant methods here. I mean, there is more than one experiment to do here. And again, I would want to lay it out in more detail than we've got here. So it's not very clear what you want them to do. If we're saying we're looking at a series circuit like this one, then we're going to need to measure the potential difference as well. So we know what the potential difference is across the resistors. So we need to show a voltmeter in here somewhere, and then show us adding in more resistors. We need to make some comment. If we are measuring the resistance across one resistor to, are we using identical resistors? Because that might be important. And then we've got the calculation here, that's fine. But I think it just needs to be a bit clearer what you want them to do. And again, with the parallel circuit, if we are measuring increasing number of resistors, we've got the current here in the ammeter, but what about a voltmeter? Where's that going to go? Because we'd need to explain that to the students. Plotting a graph of number of resistors versus resistance of the circuit. Not sure how useful that is. I think it's probably better to actually calculate the total resistance and understand that the total resistance, as you showed earlier on, is the sum of all the other resistors in the circuit. It might be more useful in the parallel circuit to show that the resistance, decreases as you add more of them in. But I think you need to be a little bit clearer what you want here. Depending on what kit your school's got, I actually just get a load of different resistors, put them in series and parallel and measure the resistance directly, but that might depend on what your school has. So your right examples do vary a little bit. We're looking here to see what the aim is. What's the aim of the investigation? Okay. Some of them it's looking at how one variable varies with another variable. Some of them it's about doing a calculation. So just make sure you're clear on that. And again, just be certain are you using a multimeter or are you using separate voltmeters and ammeters. So just make sure you're aware of that. Could be wrong. We don't use the word gotten. That's very American. And again, you're right. Students do need lots of practice. So make circuits as often as you can, because it gets them used to it, and as a teacher it makes us more used to it. Again, completely agree with that. Completely agree with that. Not electrons, can we use the word current? The electrons, it sounds like you can split the electrons up, and I'd be a little bit nervous of that. Okay. And again here, calculating resistance power, just double check. So it's not needed in AQA, it is needed at A level, so you may not need to be able to do that. Yep, that's all lovely. Yeah, these are lovely examples of starters or retrieval questions. I do a lot of these with my students. There's a lot of knowledge here that they forget, particularly around things like what is the definition, what am I measuring it with, what's measured in. So lovely stuff. Yeah, nice. And I like the fact you put them side by side so you can clearly see how they compare. Just watch capital V there. And you're right, it's called voltage. We're increasingly trying to get our students to use the word potential difference, because it's really easy for us to fall back into using the word voltage. Volts is capitalized because it's somebody's name, but ammeter and voltmeter aren't. Yeah, and in your bullet point here, you can just say it slows down current. I quite like that because it's really simple. And obviously I teach a wide range of students, so for some of them the word obstruction can seem a bit clunky, but they should all understand it slows down current. And again, I think you've got here lots of good stuff. Just watch your capitalization there. You're right, resistance is directly proportional to the length of the wire. That's nice. In fact, that's a nice link to the fact that when we're putting resistors in series, it's a bit like making a longer and longer and longer wire, because each individual bit of the wire is like a little resistor. So therefore, the more resistors in series is like having a longer and longer wire. And yes, this one's good cross-sectional area. They may not need to know that specifically, but they may need to be able to describe an experiment to find it out. Which sounds a bit odd. They need to be able to experiment but not know it, but that might be the case. And again, this is a little bit like having more and more resistors in parallel. By making a thicker wire, we know it reduces the resistance. Yep, this is all lovely, and again, really nice to see an example given there of how to carry out a calculation using that equation. Okay, again, just look at your aim here because it's overcomplicated. An aim should simply say, how does the independent variable affect the dependent variable? So we don't need to say any of this because that's not part of the aim. The aim is to investigate the factors affecting the resistance of an electrical circuit. And again, I'll break that down. I would have an aim for one experiment, say how the length of the wire affects the resistance of the wire, because that's actually what we're investigating. Again, we don't have to capitalize everything along here. Circuit set up with connected varying length of wire, yeah, and then you can see, because you've mentioned length here, that's what we're talking about in the aim. The aim should always say, how does the length affect the resistance, and then that's it. We're measurement, we're taking also length. So we're measuring the current, the potential difference, and the length. And then we're going to calculate the resistance using V equals IR. That's correct. So again, with the method here, we need to add in some detail about, I would start with the wire at a length of 1 meter, and then I would change the length to, for example, 80, 60, 40, 20 centimeters. We need to state whether or not we're going to repeat those readings or not. So we need a bit more detail in here. And the way to think about a method is, if I wrote that down and gave it to a student who'd never seen it before, would they be able to do the practical from those bullet points? And if the answer is no, then we haven't given a proper method. Okay. And the way to check this is, when you're teaching this, I usually get the students to write out their method with me, particularly when they're younger and they're practicing. And then whenever they ask me a question, I always say, what did you write in your book? Because if we've written the method well, they don't need to ask me the question. And again, that's making them more independent. Right, we've got plot table. So we're going to have a table showing the length of voltage in little v, current resistance. And don't forget to make sure we know that we're calculating the resistance. And resistance versus length, yes, small letters there. Safety, absolutely. And again, just make sure that the students know that we are always plotting resistance because it's dependent against length on the x-axis. Yeah, this is good. And it's really important that you use the word directly proportional here. You notice that we came across that earlier on in the topic, and that word directly proportional is really useful. And we can also use the word ohmic there. So the students make that link between ohmic, directly proportional, and the straight line graph. You can actually do an experiment where you get a piece of wire, as we did in the previous one, but you don't change the length. And instead, what you do is you use something like a variable resistor, and you use that to change the current and voltage in the circuit. I'll put an ammeter in here, for example. And when you plot the results, you do get a straight line graph, quite a nice straight line graph. And we usually do the positive bit, but you can actually get them to change the battery around then and get the negative part of the graph as well. It's a really nice way of demonstrating that the wire is ohmic. Excellent. Yeah, it doesn't behave according to Ohm's law because it's not a straight line graph, which is great. And you've mentioned here the important bit, resistance increases as temperature increases. And then you may or may not want to get the students to think about the fact that the particles in the wire are vibrating more and therefore they're impeding that flow of electrons. And again, you can do a nice experiment where, just like with the other one, we put a variable resistor in, go through a filament bulb, and then put an ammeter in here, voltmeter in here, and we can plot an IV graph, don't forget current up there, for a filament bulb, and you do get a nice S-shaped graph like this. Excellent, good, known ohmic conductors, that's all looking good, nice graph there. And again, I like the fact you put the LEDs in here. Again, if I do this in school, I do an experiment very, very similar. I start off by just getting to put an LED in a circuit and realize it only works in one direction. And again, you can then do a nice little experiment with a light emitting diode, an ammeter in, put a voltmeter in, and get them to actually plot this graph. And this is quite a common GCSE question, so getting them to actually do it is great. And get them to practice the graph, because what they're really bad at doing is they don't do this nice curve here. They'll do sort of weird straight lines in graphs, so it's a nice one for them to practice. Yeah, and you've sort of described what I've described here, which is really nice. But as I said earlier, you don't just have to do it with a resistor, you can do it with a filament bulb, with an LED. It works with all of them, so it's really worth doing that. Lots of opportunities to do practical and graph drawing. Yeah, all correct. This is a really good opportunity to do what you did earlier and actually put these side by side, because the brighter the light or the hotter the temperature, the lower the resistance. And it's a really nice way of saying to the students, this is about having more energy, more light energy. This is about having more energy, more heat energy, but basically increasing the energy lowers the resistance. And of course, what we're really doing is we are increasing the current. Add the bit about increasing current. Students are really bad at making that link, because of course what we're really doing is the energy is increasing the current, which in turn reduces the resistance. It's the exact opposite of what we're seeing happening in the light bulb. And of course that's because light bulbs are made of metal filament, whereas LDRs and thermistors are semiconductors, so they act in a different way. But you can just make that little point. With the graphs, it's really worth making a big fuss about the graphs, because we're always looking at how resistance depends upon, in this case, light level in lux, or in this case it's exactly the same graph, but we're talking about temperature in Celsius. And so in both graphs we end up with something that looks a little bit like this. So you get basically the same sort of shape graph. So you're making that link again about the fact that really an LDR and thermistor are the same piece of kit. It's just that one responds to light and one responds to temperature. Yeah, I'd agree that it's always good to get the students to do this practice, and this one is definitely really important, enough that there's a question on that just about every single exam paper. Again, just watch your capitalisation, they don't need to be capitals there. This is a nice one to talk about the importance of accuracy, so trying to get a value or a result which is close to the true value. Yeah, I'd agree with that one. It's funny how you can get them to do a load of calculations and then they don't do it when you're doing a practical, so that's a good one. And with this one, I'd agree that with the diograph, I mentioned earlier about getting to practice drawing those graphs, because for some reason they draw lots of weird straight lines, so I'd agree with all of that. Yeah, all good stuff, and a good starter question, because that leads in beautifully to AC/DC. Yep, lovely voltage, or you can use potential difference. And I know I'm bad at remembering to do this, so it's a good thing to try and get them to do that as much as possible. Lovely graph, and again, you can demonstrate this in school on a CRO. Yeah, very nice. Watch that capital there. And what's quite nice here with this changing direction, you can also mention the word, depending on your syllabus, between different poles. So they do talk about changing polarity in some syllabuses, but I don't think you get penalised if you don't do it, but in case you see that popping up. Yeah, and again, seems obvious, but they don't go and learn this quite often, so it's worth making a fuss about that. Okay, good, so let's get rid of that one there. Yeah, in terms of teaching it, I would say that if you can do a demonstration with a oscilloscope and plug in a battery and then plug in the mains, you can really clearly see the difference. And that's where you can start getting students to think about, as you've started off there with a battery and a power supply and the plug, are very different things. So if you can do that demonstration, it's really good to do that. And definitely this one, I always get students to wire a plug. It's a good life skill if nothing else. Okay, so we need to have a mains plug. What's your spelling here? Because it's in England, we won't want to see an American spelling. I know depending where you've picked up English, you might have American spellings. But yeah, the kids will point it out if nothing else. So we always spell colour with a U in. And again, that's all good. Okay, just a couple of things that are worth noting. Again, depends on your syllabus. They might want you to talk about the fact that the live wire oscillates between plus and minus 230 volts. The earth wire should be at 0 volts. And here, carries the current away. We talk about it going through a low resistance path. And they may want more than just a fault, but if the live wire becomes connected to the casing of the appliance. So if I was to touch the outside of my metal kettle and I was attached directly to live, and the idea is the low resistance path is the wire down to earth rather than the high resistance path, which is me. So the earth wire protects the user, whereas the fuse protects the appliance. And I think you mentioned earlier on, but it's it will encase 2 words there. If too much current flows, the fuse melts, which is perfect. Okay. Yeah, very nice. What I quite like about your 2 diagrams is then we've got the pins here, and then we've got the cables. Students get a bit confused about that, the idea that the pin is the metal bit and the cable is the wire. So it's quite nice to see those done side by side. Yeah, this is all good. Just this one, I would say less likely to be found in any bathroom area because of water hazards. Most likely to be found under the stairs. Again, depends on the age of your house, but quite often there's a cupboard under the stairs and quite often they're put there. Yeah, very nice. And you've mentioned metal here. It's really worth just emphasising the fact that plastic appliances in the UK don't have to have an earth wire, but metal ones must. Yeah, very nice. Again, I like the fact that you show where this equation comes from, which is nice. On PowerPoint, if you highlight the bit you're interested in and go to font, you can get a squared as a superscript. If you have a little look, you'll find that way. If you're doing PowerPoint slides, I would try and do that because although there's nothing wrong with what you've done, it's trying to get students to use indices correctly because otherwise they muddle up squared with like CO2. This is all nice. Yes, they do. At the moment, weirdly, they don't have to record. They haven't had to since COVID, but that might come back. So I don't know whether that's still going to be true by the time you start teaching. And yes, I would agree. Lots of questions here. Units, absolutely. And I think getting interest, I think every time you make a link with what they're doing to real life is powerful. And that's why things like teaching them how to wire a plug and how to interpret circuits and talking about it in the home, I think is very powerful. Okay, again, just check some capitalizations here. We don't need the capitals there. That's fine. If energy is not useful, then the energy is wasted. That's how we define it. So if what you mean is it's gone somewhere else, that's fine. Efficiency of the energy, that sentence doesn't make sense there. If you mean the energy transfer, they're almost never 100%. So just be certain what you mean with that. Okay, power calculation, again, really nice, nicely laid out. Okay, yeah, nice definition, absolutely. Just again, what's your capitalization? I don't think you need it at all here, but if you're going to go for it all the way through. So we've got a bit of up and a bit of down. So I would have all of these just as lowercase. Don't think we need them in there. Again, we're just making sure that we're demonstrating that to children. Step up transformers increased, absolutely. I think on your next slide you talk about that in a bit more detail. And then again, either all capitals or all lower. These are true. When you come to teach this, it's worth taking a bit of time on this because it's something that we sort of gloss over and the students don't really understand. And I might talk about it a bit more in the next slide where you're looking at those transformers and where they are and what they're doing. Okay, so just having a quick look at this then. I find using a diagram like the one up here is really useful because I can talk about the fact that I've got these two types of transformer, a step up and obviously this one is a step down. And just showing it in the context of the national grid. So if power is constant, link that back to what you said on your previous slide because that is true and those equations on the previous slide. So if I increase the voltage, the current decreases. So it's just worth here that what we're doing here is reducing energy losses. So on this diagram, I quite often just say we're reducing energy losses here. And it just makes that point, as you have here in your text, that between the power station and the house, I don't want to be radiating lots of heat out into the atmosphere. And then it's worth mentioning at the step down, obviously that's to make our supply safer. And I say safer, not safe, because obviously we don't stick our fingers in the 230 volt sockets because it's dangerous, but it's less dangerous than the alternative. And in terms of voltages or potential differences, then it will leave the power station at, and this is approximate, it always changes slightly, but tens of thousands of volts. It goes across country at hundreds of thousands of volts. Again, I'm saying 300,000. It's not necessarily 300,000, it's a few 100,000. But of course, it's 230 volts once we get here. So it just makes that point that we're racking the potential difference up really high. We definitely need to bring it down a lot before it goes into the homes. Okay. Yep, that all looks yeah, nice summary. I like the fact you've highlighted the fact it's insulating materials because again, students are terrible about doing that. Um, so that's a good thing you put in there. So yeah, that keyword is lovely there. The fact that electrons are moving is good. Um, and it's really worth just making that link actually between those two ideas. So the idea that it has to be an insulating material because the electrons will be moving through a metal. I need the electrons to be static. So it's the electrons that are static. Okay. So when I rub the two things together, I move them from one place to the other because they wouldn't move normally in a metal. And lovely that you've moved in and talked about friction there. Great, very good. Yeah, nice example. I've just added a video that I quite like, the Science Shack, um, because you can actually see them using Tesla coils to make nice big sparks, and the kids usually like that. Um, I think because you've mentioned in your previous slide really well those ideas about friction and movement of electrons, I would include that here. So you said here ionization. I'm not sure the students would understand what this means, but the idea, and it's explained quite nicely in this video, that you've got different sized particles rubbing past each other. So you can talk about the friction and the fact that that's where the charge builds up. I think that's really worth having a look at. Okay, and then that makes that link back to your previous slide. Yeah, this is a nice activity to choose. Kids always love doing this. It's a lot of fun. So yeah, absolutely do lots of this. Yep, another nice activity. I like the little diagrams at the bottom as well. One thing just to point out when you come to teachers, don't let them call these north and south, and don't let them get to magnets and call it plus and minus, because obviously those two phenomena are very similar, and the students model them up in their minds. So just be aware when you teach magnetism that you absolutely make that break between those positive and negatives and north and south. This is a good one, and it's worth finding a really nice explanation as to how the Van de Graaff generator works. Because again, you can talk about friction and the movement of electrons, but there are some really nice videos out there that demonstrate exactly what's going on. Yep, nice examples here, particularly the everyday applications. They used to be examined, but they're not anymore for some reason. But you might see those in old papers or different exam boards. It can be worth as well. I like the fact you talked about the dangers. You can actually link them to some real life examples. Most of them will be able to find earth wires under the sinks in their homes, and of course that's because the water rubs against the metal of the pipe and can cause a build up of static charge. And then aircraft refueling is a really common one. As the fuel moves through the pipe, it rubs against the edge of the pipe, and static charge will build up. Obviously not great with aircraft fuel, so we have to earth those. And there's loads and loads and loads of examples. Operating theatres is another nice one. Yeah, lovely. I mean, nice. You're ahead of me there. I obviously hadn't read enough with your slides, but absolutely spot on. It's a really common misconception, so I'm really, really pleased that you've noticed that one. Yeah, really nice. I'm not sure if this is the word you mean, invincible. Don't think that's quite right. The lines don't cross, absolutely, and they always go from north to south. One thing that you're missing from your diagram, which they must always have, is arrows. Okay, so if students draw this in their books, I always make them put the arrows on. They must show north to south. That's an absolute must. The less is the more yeah, agree with that. And in fact, another nice way you can put that is that obviously at the poles, that's where the lines are closest together. So rather than maybe the more lines, the closer the lines is perhaps a better. Or we talk about there being a density of those field lines, a field density. Not sure what you mean by lines should be evenly distributed. Whether you mean because they're not really here. So just make sure you know what you mean by that. Okay. Again, we do use magnetic fields, but I wouldn't mention them here. I would look at them separately so we don't get that muddling up of electric fields and magnetic fields. There are lots of overlaps. But at this stage, as you said earlier in one of your slides, we need to make sure they learn about them separately. So when they come to put them together at A level, they've really understood what's different before they look at what's the same. Okay, again, we do it to capitalise. These are definitely correct, but easier to say that the field lines go from positive to negative. It matches up with what you mentioned earlier on about the convention of a circuit going plus to minus, even though we know the electrons go from negative to positive. So we always draw field lines from plus to minus. So if I had 2 point charges close to each other, then I would show the field lines going from plus to minus. So that's why they appear to come out of the plus and into the negative. And yes, absolutely. Yeah, uniform field, agree with all of that. Parallel charges. And then again, this is nice. The lines go from positive to negative. Just be careful here. With a uniform field, they should be straight and parallel, but we need to then recognize that in the diagram, they're not looking straight and parallel until you just get this section here. So if you're using that diagram, just make sure the students understand that in the main section between those two parallel charges, the lines, the field lines will be straight and parallel. But as we get away from that main section, they start to bend. Okay, so either do that or don't use a diagram like that, show one that just shows parallel lines. Yeah, I like this without being in contact, because this then links up with a bit of forces where we talk about contact and non-contact forces. So it makes that point really well. And of course, that's the whole thing about being in a field. Fields exert forces without things necessarily being in contact, whether we're talking about electric, magnetic, or gravitational. Okay, good. And again, maybe session rather than lesson there. Yeah, nice. Again, using that table makes it really clear. You and the students can compare those different properties. So excellent. Again, so I've just included, again, something that I use just because I didn't see the pictures of particle arrangements within this section, and I think it's really important to cover that. Again, I've just sort of shown here, this is just something I use here with my classes, but what I find is they're very good at doing this diagram here for solids, but they often make mistakes with the liquid one. They show the particles spread out, which of course they're not, because it's incompressible. The particles need to be touching. There's just enough space for them to swap places and slide past each other. And then with the gas one, what I quite often find is they draw, for some reason, tiny particles. And of course, they shouldn't be doing that. They should be drawing the particles all of the same size. So I always make sure that students have got this really securely before I move on to talk about the next aspects of this particular part of the course. Yep, all good. I would add actually that density is how heavy something is for its size. And I think that's because it's really easy to demonstrate. So we have a set of blocks at school, and I get them to hold a wooden block which is the same size as a lead block, and they can really clearly feel the difference. So how heavy something is for its size is perfectly fine to describe density. And again, nice showing the demonstration there. I would find on your PowerPoint how to do meters cubed rather than this thing here, because again, I think it confuses students. But I like this bit here, getting to show that. You'll find when you come to teach it that students aren't very good at working out the volume of a block, because they do it in theory and maths and then don't move that to the actual practical example in lessons. Yeah, these diagrams are fine. I'm not quite sure I like the word moderate. I think it's just that it's less dense than a solid. But we also have to bear in mind that solids don't all have the same density because their molecules and atoms aren't all arranged in the way shown in that diagram, because obviously they're all very different. But again, this is quite a nice one for showing that we need to show the particles to be the same size. And then this is all fine. Yeah, agree. I'd monitor very carefully because they make a lot of mistakes when they first start out. Yeah, and that's fine. Definitely agree with what you said about units there. That's all good. Just watch this. The plural equipment is just equipment. Yep, all good. Okay, again, if I was turning this into an aim, the aim on this particular required practical is to find or determine the density of ... And we do two at GCSE. One is a regular object and the other one is the irregular object, as you've said here. So rather than saying investigating, we're determining, we actually do a calculation. And that's different to investigating, for example, how does the density depend upon temperature? So whenever we look at aims, we're either looking at how this variable affects that variable, or we're determining something, the density of, specific capacity of. Yeah, nice summary here. I like the fact you put the three different practicals here next to each other so you can see the difference. And I do like the fact you've mentioned things like, we do the mass while the object is dry. So really nice. Okay, yep, nice definition. That's all correct. And a nice summary down here about the different energies. I put a couple of slides in next, which I'll just show you again how we sort of look at this with the students, just to sort of introduce the idea of internal energy to them, because they find it a bit difficult to grasp. It's not an easy concept to understand, really. So I'll just show you that and see if that sort of adds a little bit more nuance, if that's useful. So I usually do a quick reminder that we need to add or thermal energy, or increase the thermal energy store in order to go from solid to liquid to gas. And then when I've done that, I ask the students what energy store is increasing for the particles, and then we talk about the fact it's the kinetic energy that's increasing, and that's a nice lead in then to looking at internal energy. So then we go into this idea that as the thermal energy increases, we've already mentioned that the particles are going to gain kinetic energy, but because they're held together by bonds, which we can represent by springs, then as we increase the temperature, the energy increases. So as well as moving faster, the springs get stretched, if you like, the bonds, the energy within the bonds increases. So as well as increasing the kinetic energy, we're also increasing the potential energy of the bonds, if you like. So now we're introducing the idea that internal energy is a sum of both the kinetic energy and the potential energies. And that's the definition they need to learn. I also take a bit of time to explain the word system. So the idea the system could be the air in this room, or the hot water in that kettle, or the gas in a jet engine, just to get them to understand that the word system, which sounds a bit vague, actually has a specific meaning. So hopefully that's a useful way of thinking about it. Yeah, this is all good. I would just explain to the students what delta means, because they may not have met it before. And the idea is change. You may also see MC delta theta. Some people use theta for temperature. Just depends on what board and what they like using. Yeah, nice example. And again, nice showing that you write the equation out and put the numbers in. I like the fact that you've talked about the conversion to kilograms, because of course in chemistry they use grams. Obviously we're right in physics, but that's how it is. Yeah, this is all correct. And nice about the fact you're introducing this idea that when the change of state happens, we're no longer increasing temperature, but the internal energy still does increase. Again, you've laid out the equation really nicely. Yeah, this is nice. One thing that can be quite useful as you've done the graph, and when you do this for real, I would join the dots and get the children to show the graph like this, because you can see really clearly there, as you've described, that B and D will again change of state. It can be useful just to point out that in sections A, C, and E, we've got an increase in temperature. And because we've got an increase in temperature, that's related to E equals mc delta theta. So the temperature is changing, and the energy required to do so is the mass times the specific capacity times the change in temperature. And when we're at B and D, where we're changing state, then that energy is now related to E equals m times L, because that energy is now changing state, not increasing temperature. So in effect, these flat sections, those two equations are important, and any time when the temperature is increasing, then E equals mc delta theta becomes important. And it's just a nice way just to think about why we've got two different equations, because they relate to different processes on the graph as well. Okay, nice summary of pressure here. It might be useful just to remind yourself, obviously, to put these in superscript. It can be worth reminding them that they may have met things like centimetres squared in the past, but they would need to convert that to metres squared at GCSE, because now we're only working in pascals. Whereas at Key Stage 3, they might have been allowed to have things like newtons per centimetre squared, newtons per millimetre squared, without the need to convert to pascals specifically. Yeah, this is all good here and here. Could phrase this slightly differently here. Really what we're saying is that we get a change in velocity as a result of having a resultant force. So that could be a little bit less clunky, but that's fine. Rather than saying gas producing force as though sort of manufacturing something, really what we're saying, it's a sum of the effect of all these collisions. Okay, so just make sure you have a look at that. And again, this equation is all fine. It's just worth making sure you relate it back to F equals ma and Newton's laws, because then we can talk about the fact that what we're really looking at here is mass times the change in velocity. So at some point it's really worth deriving that. And then look at the last bullet point here. Yeah, that's fine. I'm not sure how much of that they really need to know at GCSE, but that's all fine. Yep, all good. Nice illustration of the graph there. Check the syllabus when you come to teach. Some of them actually require the students to know this is Boyle's law. Some don't, so just double check that. And some might ask you to include this question. Usually, always used to be A level, but have a look at the new syllabuses at GCSE, because they may require you to know that one. Lovely, and nice showing that graph going down to absolute zero. It is worth, when you come to teach, explaining what absolutely zero means. I do that at Key Stage 3, but depending on what your school syllabus says, you may or may not need to go through that. And again, it can be worth just remembering that your syllabus may or may not require you to share this equation with your students. And of course, this is the Gay-Lussac law, used to be just known as the pressure law. Yep, lovely. And again, you may or may not be required to tell the students it's Charles's law, depending on your syllabus. You may or may not need to include this equation. Again, depending on your syllabus and if it's combined science or physics. I do like the way you've left the graph here. That's nice. And you can get the kids to discuss that, you know, what happens at zero temperature. Well, if it goes down to zero volume, that suggests that there's nothing there, which of course would not work. Yeah, very nice summary here. Again, just watch out for a little bit of consistency here. I would do this so that the two sides look the same. And we don't need to capitalize bicycle there either. Probably not room temperature, so just keep an eye out for those. Yeah, I like these examples, the fact we can do work on gases, or that gases do work. the idea that we're looking at internal energy. You can relate this back then to this idea that if internal energy is the total kinetic energy and the total potential energy, then obviously we talk about what happens to the kinetic energy here, but obviously as you're compressing it, then you are adding energy in terms of potential energy as well as kinetic energy. So it's a nice one to make a link back to a previous part of the course, and of course the same on the other side. Nice stuff. Yep, lovely. Again, when you come to use this with students, make sure that these are subscript, just because they need to understand it's not P times 2 and V times 2. And again, if you have a look in PowerPoint on the font section, you'll find where you can do that. Nice example. And again, I do like the way you lay out your working. It's really clear and models brilliantly what the students should be doing. Yep, this all looks good. It's a really good time to use some images here, I think, particularly when you come to teach. I've just put 3 on here that I use as part of this unit. And I've also just stuck a video clip link here. I quite like this one. It's of a diver taking a bottle down. And I think that can really bring to life what you've put here in your bullet points. So, yeah, good stuff. Yeah, this is all good. It can be a nice opportunity to derive the equation here, and particularly if you've got an upper set. So if I've got here, I'm looking at 2 kinds of energy, so GPE and work done. Obviously they're equivalent. So if I've got work done is force times distance, and GB equals mgh, we also know that density is equal to mass divided by volume, therefore mass is equal to rho times V. So I've now got force times distance equals rho VGH. If I divide by volume on both sides, I end up with rho GH on this side, and of course distance divided by volume is area, so I've got force divided by area, which we know is pressure. So quite a nice one to do if you've got a good set. Yeah, this is all good. Students might ask you about the difference between buoyancy and upthrust, because they are used interchangeably, and obviously we've just looked at the buoyancy equation in the previous slides, always been known as the buoyancy equation. So basically upthrust is the force that's exerted upwards, which, as you said, is going to be affected by the density and the volume of the object surface area, but also the density of the fluid it's in, so don't forget that. And the buoyancy is its tendency to either rise or sink or float. Okay. And then with hydraulics, yeah, it's really important we go back to this idea of liquids are incompressible. You can have pneumatic systems, but you have to compress the air to get the same incompressibility. I completely agree with your comments here. I would say that teaching this before you teach things like velocity and acceleration is difficult. And certainly we would normally teach this towards the end of any unit, which looks at both energy and mechanics. So I think you're absolutely right. Yes, all good. And it's worth just noting here that we put that in the context of things like the plum pudding model as well. Okay. And other models. So when we explain Rutherford's experiment, it's sort of talking how that is part of a continuum of experiments and understanding. Yeah, very nice. I particularly like this idea that you're showing a timeline and the theory and the issues. That's really nice. Very nice comparator here. Again, nice continuation here. I would just make the point that with the nucleus, we also need to make the point it's very small compared to the size of the atom, because otherwise the findings of Rutherford's experiment wouldn't be what they were. So just make that point there as well. Yeah, I've just moved your slide up here because I think it flows better if it comes underneath your discussion about that sort of progression of our understanding of the atom. So, and going back to what you said earlier about the order in which we teach things. So this is all looking good. And I would just say when we're teaching kids, we try and make the point that the you said here what happens. Let's get rid of that capitalization there. And of course, we expect everything to go through. It doesn't. And it's this idea that the only way we can explain the small number of high deflections but the large number of small deflections is that there must be a nucleus where most of the mass, okay, which must be positively charged because it's repelling the alpha particles, and it must be in a very small, it must take up a very small percentage of the whole atom. So the nucleus is small where most of the mass is, and it's positively charged. So just make sure we make that clear, because that's what students need to take away from the experiment. Yeah, excellent. And again, check each syllabus depending on what your school teaches, but most of them require them to know, if not all of this, certainly the first 2 bullet points. Yeah, very nice. And again, just nicely summarised here, the key facts that they need to know. Yeah, nice points here. And certainly for bullet point 1, I use Cognito. They do a maths section, which I find really useful for going through standard form with the students. And the other one is Corbett Maths. I might have spelt this wrong. I think it's got 2 T's in it. They do some nice videos as well. So you could use those if you're not sure if your students have got to standard form when you get there. Yeah, all very good. Just make it really short. Overemphasize the fact that we're talking about atoms here, and then compare it with chemistry, where they learn about the difference between atoms and ions, because it's really important they know we're only talking about a neutral atom when we make these statements. Just helps your chemistry colleagues. Yeah, this slide all looks really good, and a nice layout explaining how we calculate the number of neutrons. Okay, so this is fine. Just watch nucleon here. Nucleon is the number of atoms in the nucleus. So actually the nucleon number will change if I change the number of neutrons. So the nucleon number isn't the number of neutrons, but the number of things in the nucleus. And then the rest of this all looks fine. Nice to make this little link here. Yeah, this is a nice example. Students do find abundance a difficult idea, so having examples here is a good idea. In fact, this was an exam question quite recently. And again, really nice about that idea about same element, different mass, and the more you can link type of element to number of protons, the better. Yeah, these all look good. Just watch your use of language here, irradiation. You could either say plus radiation or a particle. So just make sure that's clear here. Radiation we think of quite often as being a wave like infrared radiation or gamma radiation, and that's different from this. This is actually matter here. So in this example, we're looking at something which would have mass and charge, whereas say gamma and other kinds of radiation wouldn't. So just be a little bit clear here. This one's really nice. This one's really nice. This is good, yeah. And I think it's a good use of the word nucleons here. That's used better there, which I like. And again, I like this one here. And of course, you can show that on the periodic table, where as you go down the bottom of the periodic table, you've got more radioactive elements on the periodic table, and you can clearly see the big difference between the numbers of protons and neutrons. Okay, this is all looking fairly good. Just watch, you don't need to have a capitalization of helium there. And if I were teaching this, I would do this a lot more slowly. I'd sort of break this up a little bit more into more stepping stones, but you're absolutely right. 2 protons, 2 neutrons. And I would talk about the mass number rather than the nucleon number. That's probably a more useful one. And yes, the proton or atomic number down by 2. Just make sure that you're using both of those terms as well to make sure that students make that link with their chemistry lessons. Beta particles looking good. During nuclear equations, the nucleon number of the parent nucleon has no charge. That doesn't make sense there. and the proton number +1. I think the problem is you've tried to explain quite a difficult concept here. Yes, you're right, the atomic number does increase by 1. There's no overall change in mass. That's the key thing to put here. There's no change in mass, but the proton number goes up by 1. And obviously then need to explain what beta radiation is and why that happens. And yes, high energy electromagnetic waves, no change at all. And that's of mass or atomic number. So it's really important we make that clear, because obviously there is a change. That's why the gamma radiation has been emitted, but the emission of the gamma ray doesn't have any impact on those two properties. And looking at the neutron release, that's not in every single syllabus, so you may not have to teach that. I have a feeling it might crop up only in some of the physics only courses. Yeah, so just going on from what you were talking about on the last slide to do with beta radiation, it's just really worth making that clear to students. So obviously we know that beta is an electron, and obviously there are no electrons in the nucleus. So the first question I usually ask students is, how do we get an electron out of a nucleus when there aren't any electrons there? In which case, I mean, I usually do the example of carbon-14 because it's a relatively small number of nucleons to work with, whereas obviously when we're looking at other ones, 1, 2, 3, 4, 5, 6, 7, 8. So if this was carbon-14, then I would have the 6 protons, because carbon has got an atomic number of 6. I'd have 8 neutrons. And what we know is that there's no electrons there. So instead, a neutron becomes a proton plus an electron. And obviously, protons are positive, electrons are negative. So there is a conservation of charge there. Now, this equation isn't complete because at A level they would learn about the fact that you lose neutrinos when you have this sort of decay. But for GCSE, it's really nice because you can point out that if this has got a mass of 1, this has got a mass of 1, and this has got a really, really tiny mass, then there's only a small change in mass. And again, at A level, they start to learn that that mass is related to energy in terms of E equals mc squared, which obviously is Einstein's equation. So in that case, I've now got one of these neutrons has gone because it's now become an extra proton, and then the little electron that's released as beta radiation. And when I go back to my nucleus, I've now got 7 protons and I've got 7 neutrons, and of course that would be nitrogen, and those 7 neutrons, adding those together gets me to a mass of 14. So carbon-14 decays to nitrogen-14. If you've got an upper set, it's really worth showing them that so they can see why those numbers change. Yeah, again, a nice way to lay this out. Again, just watch some of those capitalizations. We don't need to sort of put capitals everywhere. There's a couple down here as well that I saw, I think thick lead and so on. So we don't need those. But otherwise, this is a really good way of getting the students to compare what they're learning. Yeah, nice summary. And again, depending on your syllabus, you may or may not need to go to this much detail. Yeah, nice discussion. I mean, the big thing, as you're absolutely right here, is safety and making sure that you're properly trained before you use any radioactive sources, or that you have somebody else in the room to demonstrate them for you. So absolutely spot on. Yeah, this is nice. I would just make sure that I would have the numbers here as well, because what we're really looking at when students are doing these calculations is that 219 should, when I get to this side, the 2 numbers on this side should add up to make the 219. So we're sort of balancing the equation, if you like. So in this case, if I put my 215 in here, 15 plus 4, you can see equals the 219 here. And again, if I've got the 2 here, we can clearly see that 2 plus 84 equals 86. Okay, so yeah, I would always show that as I go along, and then your demonstration there is lovely. And just the same thing here, I'd put the numbers in here because again, as soon as you get down to this end, you can see that 7 take away 1 equals 6. So again, everything's balanced, and then 14 equals 14 plus 0. And again, just pop these in here. Otherwise, your demonstrations are laid out lovely. Brilliant. Yep, this is really nice. Just watch here. I don't really want to describe radioactive stuff flying. I think you mean off the material there. We ought to say it's emitted. That's the correct word. Otherwise, they have this idea of little particles flying off the surface, which is perhaps gives them the wrong image in their heads. Chance of decay for each atom, not quite right. The chance of decay is always 50-50 during each half-life. So if the half-life were 2 days, each atom has a 50-50 chance of decaying within those 2 days. So at the end of 2 days, half of them will have decayed. So it's probably better to say the activity depends upon the half-life. So the shorter the half-life, the quicker that activity will reduce. And then Becquerel, nice, very good. Okay. Yeah, I like we say here doesn't actually start at 100, and while you've got a graph, this is a really good time to demonstrate it. So if I'm looking at here, you've done percentage of remaining nuclei. So if I wanted to go from 100 to 50%, then I can read across and find that the half-life here is 2 days. And if I were to go to 25%, somewhere around about here, it would line up with 4 days, and therefore we can see that every time I go the same length of time across the bottom, I'm halving along the y-axis. And when you come to teach, it's really useful to change the y-axis here with percentage, number, activity, so they can see that it doesn't matter what you're measuring, it always halves. So when you say half-life on the graph should be the same, I think that's what you're referring to, so I would always demonstrate it in that way. Okay. Yeah, it's good that you've looked at the sources. That's really useful. And I might make a little bit more there about the idea of background radiation. So this idea that this exists anyway, and that a lot of it has got nothing to do with us. So the idea that this section here is what we produce and everything else is already sort of produced anyway, so therefore we've evolved to live with a certain level of background radiation is good. I would make a little bit more of these when you come to it, because they feel like a really tiny bit of the syllabus, but they can generate really long answer questions in an exam. So I would say on or in the subject, because of course we could eat it, for example, or if we're using it medically, we might inject it into our bodies. So although we're doing it deliberately, it's still a contamination. And the idea is that the subject is now radioactive. So if I have, I don't know, swallowed a barium meal, for example, I am now emitting radiation from within my body. So it could affect me, but also anybody else around me. And it's difficult to remove contamination. So if you've got it on your body, it's difficult to clean it off effectively. And if you've eaten it, obviously it's difficult to get rid of it, which is why we only use sources with very short half-lives, and why something like polonium would kill you if you ate it. And then irradiation. I think the key here is when we're saying absorbed by, we just also need to make it clear that the subject does not remain radioactive. So as soon as you switch off the source, the radiation is no longer there. So a good example is to think about a torch. If I were to shine a torch on you, the light would shine on you, you'd absorb the energy from the light, but the minute the torch is switched off, there's no longer any radiation there. So therefore, it's easy to be safe. You can either switch the torch off or put something in the way. So it's easy to avoid the radiation. So you don't become radioactive if you are irradiated. So we could irradiate hospital instruments and kill off all the bacteria, but the hospital instruments are not radioactive. They're perfectly safe. Yeah, good stuff. Okay, so little h there, like it is a helium nucleus in effect. What do you mean by ionization potential of +2? It's got a charge of +2 and it is the most ionizing particle. That's partly because of its size as well. Its kinetic energy in effect, because it's the heaviest particle, and if it's, depending on how quickly it's moving, then it's going to have a lot of energy that it can transfer. Again, just watch the capitalization there. And yes, it only travels a few centimeters. Interestingly, each syllabus has a different number rather than 8. But yeah, a few centimeters. Again, don't capitalize the skin there. Beta particles, yeah, 1 electron. And again, that's its charge. It is less ionizing. It can travel a little bit further than that. Check your syllabus. Ours says 1 to 2 meters, but yours, it may say less than that. But it's sort of between, up to a meter. Stopped by metal foil, good. You might also mention there thick plastics like perspex can also reduce or stop beta. And then gamma rays, good. Just careful with photon. They may not have met that before. It definitely travels the furthest. And stopped by thick lead or concrete, absolutely, or a combination of both. The least ionizing. Okay, it does ionize, but it's the least ionizing, which you make more clear in, I think, this bullet point here. Yeah, good, a small c there. Nice that you've got their mutations. That's a nice link as well with the biology syllabus, which is nice. And yeah, I think here, just put the risk here. The risk of ionizing radiation causing cancer does depend on things like the dosage. You're absolutely right. It also depends on where it's absorbed. So there are certain organs of the body that are more likely to be damaged by higher doses or lower doses. So you can look at things like Becquerel, Sieverts and Grays for that. Again, it depends which syllabus you're teaching as to whether or not you need to go into that level of detail. And again, this one's really nice. Yes, cell death, and it can be cell mutations. Good. I like the fact you use here decay, which is nice. It's measured in becquerels. Good. Which is counts per second in effect. Just watch out with it. What do you mean by that? Do you mean that radiation has uses and dangers? Okay, just make sure that's really clear if you're teaching. Higher activity in terms of counts per second. Okay. Yep, this all looks good. And I like the fact you've gone through different things we can do to reduce risk. That looks nice. And you can then ask the students, what's the point of a lead window, an aluminium window, an open window, and paper, and just go back and relate it to the different types of radiation, which ones it stops, which ones it allows through. Yeah, these are really nicely done. And this is a nice place where you can link back and talk about the fact that, for example, number 1, we are contaminating the patient by introducing radiation into the body, whereas in radiotherapy we're irradiating. So this one's contamination, this one's irradiation, and it's just quite nice to get students to think about the fact that if you've had technetium-99 injected into you, for example, you will be radioactive for a few hours, whereas if you are using a gamma knife, then you won't be. Yeah, really nice that you've done that here. You've talked about irradiation passes through the field. The food is not radioactive. Excellent. And again, this one's really nice. Again, this is another irradiation, so you could mention that word there. Yeah, and again, this is a contamination because we're actually putting something into the water. And this is irradiation. Yeah, really nice examples. Yeah, really good. I like that. The penetration. You could also mention ionization. So, for example, we use alpha for smoke alarms because it is very ionizing, and definitely half-life. Good. And it's really useful to get some examples and sort of say, well, things like smoke detectors, pacemakers, we want a relatively long half-life, but we want a short half-life for technetium. So, very nice. And again, this is part of the curriculum which you may or might not need to teach depending on whether you're doing separate physics or not and which syllabus. So some of this comes up, some of it doesn't. This is good, yes. Releasing energy neutrons. I can put simply in, just say it's just more likely to decay. That's fine there. Uranium, barium, krypton, lovely. Good. And then I like the equation, and again, it's quite a nice one. The only time I've seen it turn up, even as a physics only question, is they wouldn't be expecting anybody to know it, but they should be expected to perhaps put in the missing numbers or explain it. That looks lovely. Good. The exponential bit, chain reaction, little c. That's good. I think the thing with the chain reaction as well is this idea that it links to this exponential idea. So if we don't control the chain reaction, make it not a chain reaction, in effect, that's a bomb. Good. And mention how it's controlled. So you talk about maybe something like the barium rods and so on, things like that. Yeah, this is lovely. If you can get a diagram in instead, I find that it's a sort of dual coding idea. The students will see the picture and the information and link them together. Again, nuclear fusion, not necessarily in the combined science, generally only in the physics or triple GCSE science. And yeah, two thermonuclear join or fuse is a nice word to form a larger one. Yes, at extreme temperature and pressure, that's absolutely true. And it's just worth mentioning, I will check in a minute in case you put it on a later slide, but we're talking about hot and cold fusion. They both need extreme temperature and pressure, but cold fusion would occur at temperatures or pressures lower than the sun. We've not yet done it. We've had some experiments on Earth that look promising, but are not necessarily repeated. I like the fact you said not yet practical. Absolutely. Obviously, it'd be great if it were. Both fission and fusion release energy. And there's a nice graph somewhere you can pull off which shows that it's iron 56, which is the sort of turning point. Anything below iron 56, you can get it to fuse and release energy. Anything above iron, you fission it and it releases energy. But that's really a link to A level. Rest of it that looks okay. This looks good. Again, just watch your capitalization here. We don't need to have a sun, maybe not. I don't tend to, but some people do for the sun. These look good. I do like the fact that you've talked about things like safe storage, costly, still experimental. So yeah, I think you've got everything that's important in there. That's a nice comparison. Well, congratulations on managing to get your scores up so much. There's an awful lot in this unit. You'll see by how long I've been yapping on at you, the marking. There's a lot to go through, and I think to make that improvement is absolutely amazing. So congratulations on that. And you're absolutely right with your comments here. It's the what and the how to teach it. And obviously you've got plenty of time between now and when you qualify to learn the how. But at least now I think you seem more confident about the what. Interestingly, I probably agree with this. I think your maths bit was really strong. And the fact that you are laying out those calculations and modelling that is going to be really important for those kids because they are terrible at remembering to show they're working. I really like that about what you did. Yeah, I think this is an interesting one. I think the required practicals, if you've been teaching a long time as I have, they're practicals we've always done. So in that sense, they feel familiar. But putting them into an exam doesn't, because obviously until relatively recently we didn't do practicals as part of exams. They were done as practicals and coursework in the classroom. So I do completely get why they can seem a bit funny to start with. Your syllabus that you teach, as most people do AQA, you will get very good guidance from the exam board on those when you get there. And I think you're right, the video recordings probably do have overlapping and repeated material. And I really do agree with what you said down here. I think one of the problems with the VidLearn topics is the order you go through it in isn't necessarily the order you teach it in. I think you're absolutely right there. And hopefully when you start teaching in a school, you will see that they've taken time to put their curriculum in the right order. and that's not necessarily the order in which this has been done here. And you're absolutely right. Some of those bits of knowledge that we're expecting them to have that haven't been taught yet, we definitely wouldn't teach it in that order. So I'm hoping when you get into the classroom and see your schools and their syllabuses, a lot of those issues will solve themselves for you. I really like this comment. I still do that even after all these years. I think it's a really good thing to do because it does make those sort of key ideas really sink into our heads and make them a little bit more fluent when we're talking to the class. So brilliant idea. Share that with your colleagues next year. This is good. I mean, you've put a lot of effort in, and I can really see that in the slides you sent me. And I really hope that next year you will find you can come back and use this stuff. You know, nothing in teaching is ever wasted. So I really hope you feel next year that the time you put in this year has really reaped benefits for you. Yeah, these are really good suggestions here. I like these. Yeah, good. I'm absolutely delighted you found PhET. I'm a massive fan of PhET. And I would also just suggest, I really like Cognito. Um, they do physics, chemistry, biology, and maths at GCSE, and I really like Amadeus's little videos. They're all little animations, and they're great because you can freeze them and copy them and use them in your lessons. You can get the kids to use them. I also recommend free science lessons. They look a little bit drier, but what I like about Sean's videos is he really relates them to, in this case, the AQA syllabus. They are really sort of designed for the AQA syllabus, but he does a whole series of ones on the required practicals. So if that helps, you may find when you come to teach, I quite often use those for myself, but also with the students. And I always recommend those two sites for the kids. So I hope you find those useful.